The engineers said it couldn't be done. Steel had never been used for a major bridge structure. The metallurgy wasn't reliable enough. The material would fail under load. The entire project was an expensive suicide mission waiting to collapse. James Buchanan Eads listened to their objections, thanked them for their professional opinions, and built it anyway. Within a year of completion, 50 trains crossed his bridge every day. Within a decade, it carried more traffic than any bridge in America. The Mississippi River at St. Louis in 1867 presented an engineering problem that had defeated everyone who'd attempted to solve it. The river was over 1,000 feet wide at that point, with currents that could reach 8 miles per hour during spring floods. The riverbed consisted of sand and gravel down to depths exceeding 100 feet. No solid bedrock to anchor foundations. Every previous attempt to bridge the Mississippi had failed or been abandoned as impractical. St. Louis relied on ferries, and ferry operators preferred to keep it that way. The city's economy depended on remaining the dominant river port between New Orleans and Minneapolis. But by the late 1860s, railroads were changing the calculus of American commerce. Chicago, directly north of St. Louis, had become the nation's railroad hub precisely because trains could move freely without interruption. St. Louis, split by the Mississippi, watched freight bypass the city rather than deal with the bottleneck of transferring cargo between trains and ferries. The city was slowly losing its commercial preeminence to a rival that had better infrastructure. A bridge would solve everything. It would also be nearly impossible to build. The technology didn't exist for a structure that could span such distances over such unstable foundations while carrying the weight of freight trains. Wood wouldn't work. It would rot and catch fire. Iron had been used for railroad bridges before, but iron's tensile strength made engineers nervous. Cast iron was brittle. Wrought iron was inconsistent. Neither could be trusted for the loads and spans required. James Eads proposed using steel, structural steel. Not small components or decorative elements, but massive load-bearing members carrying the entire weight of the bridge and everything that crossed it. The engineering establishment reacted as though he'd suggested building the bridge out of paper. Steel production in 1867 was unreliable, expensive, and limited to small quantities. The Bessemer process that made cheap steel production possible was barely 15 years old, and still viewed with suspicion by conservative engineers who'd spent their careers working with iron. Eads didn't care about conservative opinion. He'd spent 20 years as a salvage diver and riverboat engineer, working in the Mississippi River under conditions that would have killed most men. He understood river hydraulics, soil mechanics, and structural loads from direct observation rather than academic theory. He knew the Mississippi's bottom, knew its currents, knew what forces any bridge would face. He also knew that iron wouldn't work, and wood wouldn't work. Steel was the only option, regardless of what establishment engineers thought about it. The first challenge was foundations. Conventional wisdom said you couldn't build stable piers in the Mississippi's shifting riverbed. Eads proposed pneumatic caissons, watertight chambers sunk into the riverbed and pressurized with compressed air so workers could excavate down to bedrock. The technology had been used before, but never at the depths Eads required. He planned to sink caissons over 100 feet below the water surface, deeper than anyone had attempted. Workers entered the caissons through airlocks, descended into pressurized chambers, and dug through sand and gravel while breathing compressed air. The work was dangerous in ways that weren't fully understood. Caisson disease, what we now call decompression sickness, killed or crippled workers who ascended too quickly after spending hours under pressure. Eads didn't know the precise mechanism, but he observed the symptoms and implemented gradual decompression procedures that reduced casualties. 14 men still died during caisson construction. Another 100 suffered permanent injury. The east pier went down to 86 feet. The west pier went deeper, 95 feet below the water surface, establishing a depth record that stood for decades. When the caissons finally reached bedrock and workers poured concrete to create the foundations, Eads had solved a problem that most engineers had considered unsolvable. The piers would hold. The question was whether the structure above them would. The bridge design featured 3 arches spanning the river. The center arch stretched 520 feet between supports, the longest steel arch ever attempted. The side arches each spanned 502 feet. The total structure required over 2,000 tons of steel, all of it manufactured to specifications that steel mills weren't accustomed to meeting. Eads insisted on precise chemical composition, uniform mechanical properties, and quality control that steel producers considered obsessive. He rejected material that didn't meet his standards, sending back shipment after shipment until manufacturers learned to deliver what he demanded. The steel controversy nearly destroyed the project before construction even began. The American Society of Civil Engineers, representing the engineering establishment, formally opposed the use of structural steel. They argued that the material lacked sufficient testing, that its long-term reliability was unknown, that any bridge built with steel would inevitably fail. Their objections carried weight, literally. Insurance companies refused to underwrite a steel bridge. Banks hesitated to finance construction. Newspaper editorials questioned whether St. Louis was about to waste millions of dollars on a structure that would collapse the first time a train crossed it. Eads responded by building a test rig and conducting destructive testing on steel samples. He loaded steel members to failure, documented their performance, and published the results. The data showed that properly manufactured steel had tensile strength and ductility superior to wrought iron. It could handle greater loads, span longer distances, and resist fatigue better than any alternative material. The engineering establishment remained skeptical, but the numbers were undeniable. Construction began in 1869 and immediately ran into problems. The Illinois approach, on the east side of the river, required building through densely populated areas where property owners demanded inflated compensation. Legal battles delayed work for months. On the Missouri side, contractors discovered that the limestone bluffs weren't as stable as initial surveys suggested, requiring additional foundation work. Cost overruns mounted. The original budget of $4.5 million doubled, then tripled. Investors who'd been enthusiastic in 1867 grew nervous by 1871. The bridge's design required precise construction tolerances. The steel arches rose from both sides of each span, meeting at the center. If calculations were off by even inches, the sections wouldn't align properly. Engineers used surveying techniques adapted from railroad construction, establishing reference points and checking measurements continuously. As the arches rose higher, workers erected temporary scaffolding to support sections until they were connected and could bear their own weight. In September 1873, the center sections of the main arch were ready to be joined. The final closure, connecting the two halves to create a complete arch, required perfect alignment under conditions that made precision difficult. Temperature changes caused metal to expand and contract. Wind put lateral loads on the partially completed structure. The connecting sections had to be positioned within a quarter inch of their intended alignment, then secured before conditions changed. Workers made the final connection on a cool morning when thermal expansion was minimal. The arch held. the structure became self-supporting, carrying its own weight through compression rather than depending on scaffolding. Engineers had calculated correctly. The steel performed as Eads had promised. The longest steel arch in the world stood stable, waiting for the rest of the bridge to be completed around it. The bridge opened for rail traffic on July 4, 1874. Independence Day seemed appropriate for a structure that represented American engineering, breaking free from European precedent and conservative limitations. The opening ceremony featured a parade of locomotives crossing from both directions, demonstrating that the bridge could handle simultaneous traffic in both directions. Crowds gathered on the riverbanks to watch, many still expecting some dramatic failure. The bridge held without deflecting noticeably. Within weeks, trains were crossing regularly. Within months, traffic exceeded projections. The immediate economic impact on St. Louis was transformative. Freight that had previously bypassed the city now moved through it. Railroad companies that had terminated their lines on the river's east bank now extended service across the bridge into Missouri. Shipping costs dropped. Transit times decreased. St. Louis reclaimed its position as a major transportation hub, competing effectively with Chicago for Midwest freight traffic. The bridge's success silenced critics and validated Eads's confidence in structural steel. Within a decade, steel became the standard material for major bridge construction. The Brooklyn Bridge, completed in 1883, used steel cables. Railroad bridges across America shifted from iron to steel. Eads had proven that the material worked, that proper design and quality control could produce structures more reliable than anything built with traditional materials. The engineering establishment that had opposed the project eventually gave Eads credit. The American Society of Civil Engineers, which had formally objected to steel construction, studied the Eads Bridge and incorporated its lessons into new design standards. Insurance companies that had refused to underwrite steel structures revised their policies. The bridge became a reference example, cited in engineering textbooks and used as proof that calculated risk based on data could overcome institutional conservatism. Eads Bridge still stands. More than 150 years after completion, it continues carrying vehicular traffic and Metrolink light rail trains. The steel that critics said would fail has outlasted dozens of newer structures. Modern engineering analysis confirms what Eads understood through combination of theoretical knowledge and practical experience. Properly designed steel structures can last indefinitely if maintained correctly. The bridge's legacy extends beyond St. Louis. It demonstrated that American engineers could match or exceed European capabilities. It established steel as the material of choice for large-scale construction. It proved that unconventional solutions backed by rigorous testing could succeed where traditional approaches failed. James Eads's willingness to ignore expert consensus and trust his own calculations changed how bridges were built, how materials were selected, and how engineers approached problems that conventional wisdom considered unsolvable.